Morning, students. Today we shall take up the topic of small signal analysis of BJT amplifier. This topic includes a number of small items, but very essential to understand how the amplifier and its various variations work. And let me remind you, small signal means the signal value is very small, so that during this range of the signal, peak to peak range of the signal, the BJT's various inherent characteristics are constant. You have learned in your device classes that the various parameters of a BJT depends upon its bias and its operating conditions. Now let us see. Here first is a H parameter model or hybrid parameter model of a BJT amplifier. This model you have learned in your earlier class of semiconductor device class. You must have learned it. I don't know whether at the time maybe it looked like little complicated, but it was very important. So we have to revise this small part once again very quickly. This yellow boundary line is the equivalent of a transistor or a BJT. Here, the diagram has been made in such a way the same thing is applicable for common base mode or common emitter mode or common collector mode. Any mode, the same thing is applicable. There are the two input terminals, two output terminals. If the common emitter mode, this is the emitter. So this side is also emitter, this side is also emitter. This will be the base terminal and this will be the collector terminal. I think you can remember the H parameters. Hi is the dynamic input impedance of a transistor. I do not want to elaborate because then I have to go back to your device classes. It's the Hi is the dynamic input impedance of a transistor or a BJT. And if it is in common emitter mode, we call it HIE. If it is in common base mode, we call it HIB. So this is H can act. This is a reverse voltage generated between the base terminal and the emitter terminal. Let's say this is a common emitter mode. This is a reverse voltage which applies here between the base and emitter, and its value is HRV0, where HR is a this is HR. It has got a particular name. I do not want to repeat that because we have discussed in your device classes. So this is HR, where VO is the output voltage here. So there will always be a reverse voltage here, which is proportional to the output voltage. This reverse voltage come here. You should have learned it in your transistor or electronic semiconductor devices class. This is HRVO, and this is a current generator, or you can say it's a symbol of a current generator. A current flows from in this direction to common. The value of this current is a scalar HF multiplied by I1, whereas I1 is that input current. This current, this HF, is called current gain, right? And I1, and there is always a output admittance or output conductance HO. So HI, HR, HF, HO, these are the four hybrid parameters of the transistor, and this is yellow box is the general transistor model. Conventional direction of current and voltage polarities Direction of current, output current is inward, input current is also inward. Input voltage polarity is the upper one is the positive, lower side is the negative. Here also upper side is positive, lower side is negative. And load current direction is from towards the common, from the output of the transistor towards the common. So whole diagram has been made in such a way that this is the general diagram, very, very important diagram for BJT amplifier or analyzing a BJT amplifier. Have high frequency performance of BJT amplifiers. In that case, this diagram is very, very important. You high frequency analysis without this diagram. So, firstly, this is a H parameter model of a BJT amplifier. It is nothing new. It is a replica of what you have learned in your last semester in your semiconductor device class. Now, what are parameters? HI is the input resistor. These are the four names of these parameters of a transistor. Input resistance with output short circuited. That means if the output is short circuited, then whatever is the input resistance, that I divided by II is HI, right? If output is short circuited, VO is equal to 0, so this will be 0. So HI will be VI by II. HR is named as reverse voltage gain with input open circuited. So if this input is open circuit, that means if voltage source is removed from here and it is open circuit, then the proportion of output voltage which appears to the input side is HRVO, and HR is called reverse voltage gain with input short circuited. And what is HF? HF is called forward current gain with output short circuited. That means if this is short circuited, current flows through this path only, then whatever the value ratio of input current to this current is called HF. And HO is output conductance or output admittance with input short circuited. This what is short circuited is very, very important to be remembered if you want to measure the performance characteristics of any transistor circuit. After this, so this much you have learned in your device subject. Now, let us now find out what is current gain, voltage gain, input impedance, output impedance of a transistor amplifier. Mind it, we have not defined it is a common base, common mode, or common emitter or common collector mode. It is true. So this derivation will be true for all three modes. How? Look, this current IO from here to here. Right? This current is a sum of this current plus this current. Now this current is HFII and this current is this voltage VO multiplied by this conductance HO, right? VOHO, right? So this is one current equation. Another equation, this VO is equal to, this is the positive side and current is flowing in this direction. VO is equal to ILRL, right? L and IO are in opposite direction as per the convention. Do not break convention, then you will be in soup, right? VO is equal to ILRL, but IL is opposite to IA. So ILRL is equal to minus IORL. So this VO can be replaced by minus IORL. So IO is equal to HFII minus HO into IORL. From here we get HFII, we take it on the left hand side. IO comes on the right hand side is IO within bracket 1 plus HORL. So HFII, so we get a relation between II and IO. So what is the current gain of the whole system? Is the load current divided by the input current II, right? Current gain of the system does not talk about IO and all that or HFIL. It talks about the result output current divided by input current. So output current IL by II and IL is equal to I minus IO we have sent. So minus IO by II. Now from here we get minus IO by II is equal to minus HF divided by 1 plus HORL. So what do you find? That current gain of any amplifier of common emitter or common collector or common base mode depends upon the HF and HO parameter of the transistor and the load resistor, right? So this is the derivation of the current gain of the amplifier in terms of the BJT parameters. So this is current gain. Next we go to input resistance of this amplifier. Because why we are studying this? When you design an amplifier, you can measure its input resistance, you can measure its current gain, but cross-check whether your measured output is really near to the theoretical value. These are the theoretical values. So you can now cross-check whether your design is okay or totally rejected. Now, input resistance Ri. What is the input resistance Ri of this amplifier? Is the input voltage I divided by current II. This is the input resistance of the whole amplifier. And what is Vi? Look, what is Vi? Vi is HIII, this potential drop, plus this potential. This is Vi. So Vi is replaced by HIII plus HRVO divided by II remains as it is. So from here we get I plus HR by II VO. And once again, VO we know is equal to ILRL. Right? And current gain we have seen is ILII. So from here what we get? We get IL is equal to AIII, IL is equal to AIII. ILRL, right? VL is equal to VO is equal to ILRL. That means VO is equal to IL is AIII multiplied by RL. Now, what is the input resistance? Input resistance is this thing that we have found, HI plus HR by II, and VO is replaced by this term. So this II and this II gets cancelled. So this is HI plus HR RL AI. So we get input resistance in terms of HI, HR, two H parameters, load resistance RL, which you have decided, and the current gain AI, whereas current gain is given by this factor again. So that is why we first decide the current gain, because other parameters are always in terms of the current gain. So we have got current gain and input resistance. Next, we find voltage gain. Voltage gain is this VO divided by this VI. Now, VO is equal to AIII that we have got already earlier. I'll show you. is AIIIRL, right? So VO is replaced by AIIIRL. So this, and also RI is equal to VI by II. That also you have got. RI, input resistance, is input voltage divided by input current, of course. So RI is equal to VI by II. So VI is equal to RI II. So VI you replace by RI II. Then what do you get? AIRL by RI. So voltage gain is in terms of, is you get in terms of current gain and load resistance and the resistance and RI. Okay. RI also load resistance and input resistance. Input resistance we have decided. So I'll show you here. This is the RI we got, and this is the current gain we got. So with the help of RI and AI multiplied by RL, you can find out the voltage gain. Now, the last and fourth parameter of an amplifier is the output admittance. Admittance is voltage by current, and output admittance, that means if you look from here backward into the amplifier, what is the admittance? Admittance between means what is the resistance connected in parallel between the output two terminals, right? Is current by voltage. Resistance is voltage by current, is current by voltage. But by definition, output admittance is IO by VO when all other voltage sources are shorted. That means, voltage sources are open circuited. That means VS has been removed. This is a condition of definition of the admittance and impedance. Input and output admittance and impedances. So when VS is equal to 0 and also RL is considered to be infinity, that means this is open circuited. That means we are measuring output admittance of the transistor amplifier without the next stage load resistance, because load resistance is, we said repeatedly, is not a part of the amplifier. It's a part of the next stage. IO equal to IO by VO. But IO, this current IO is, we have done it earlier, HFII plus HOVO. So what is YO? YO is this IO by VO. That means HO plus HFII by VO. This is YO. Further derivation, source has been removed from here. At that time, current II into HI, II into HI is the drop here, and HRVO is the drop here, and RSII is the drop here. And since there is no source, so total drop in this loop will be equal to 0. Right? Now, you may think that where from the current will come if the source is removed. Right? The point is that polarities has been so defined, ultimately by mathematical equation, the actual value will come out. So this is, say this is totally removed and is short circuited. Then RSII, that means this is the drop of the voltage, potential drop here. IIHI, potential drop here, plus HRVO, potential available here, all together in this loop has to be 0. From here, what do we get? From here we get II by V0, that means this II divided by V0, II both can be taken common, and you have RS plus HI is equal to HR divided by RS plus HI with a negative sign. This is II by V0, right? And this is II by this II by V0 can be replaced by this factor. So Y0 will be equal to H0 plus HF multiplied by this factor, which becomes HF HR divided by RS plus HR. So current gain of an amplifier, voltage gain of an amplifier, input resistance of an amplifier, output resistance of an amplifier, how to calculate. First, we have to find out the current gain. Then, in terms of the current gain, you can find out other values. And also, you need to know H parameter values of this transistor. Now, where will you get the H parameter values of your transistor? You have to go into the transistor manual. You have to go to the transistor manual where all these four values are given, right? So, this is small signal analysis of a BJT amplifier. And the summary of these four we have found, AI is this factor. All these factors we have found out. I have made the made this in a tabulation so that you can copy and remember. These are the four values. And mind it, for finding out the voltage gain and current gain, we deconsidered or we ignored the value of RS, which is source resistance, because source actually is not a part of your system, right? And it's not in your control. But if you know source resistance, then the current gain and the voltage gain equation slightly change. This is AI. Considering the source resistance, AI will be this AI multiplied by RS by RI plus, and this AV will be equal to AI multiplied by RL by RI plus RS. So this is the values, theoretical values of these four performance parameters. These are called performance parameters: current gain, voltage gain, input resistance, output conductance. And mind it, this deduction has been shown to you irrespective of it is a common emitter or common base or common collector mode. Now, how will you go about if it is a common emitter mode? Then from your transistor manual, you find out HFE, HOE, HRE, and HIE. In common base mode, you have to find HFB. Of course, I am sure in your device classes, you have learned the interrelations of these H parameters in common base, common collector, common emitter mode. That also you can use. Now, here I have noted a few points from your transistor manual. These are the H parameters of common base mode, common emitter mode, common collector mode of a typical transistor, right? HI, and this is common base mode is HIB, common emitter mode is HIE, common collector mode is HIC. These are the typical values. Say common emitter mode, which is most important. HI is around 1 kilo ohm. That means this resistance, approximately 1 kilo ohm. HR, this reverse voltage gain, is very, very small, 2.5 into 10 to the power minus 4. In normal calculation, day-to-day calculation, this is ignored. F, that means the current gain is to the tune of 100. But of course, there are transistors where it starts from 100 to 1000, anything. But I have taken a typical value of 100. For your practical use, you should see the transistor manual and find out the values for the transistor that you have picked up. And 1 upon HO is always very high, 2 meg ohm or 40 kilo ohm in common emitter mode, and common collector mode is also 40 kilo ohm, right? Now, values in that table, you can find out the voltage gain, current gain, input resistance, and output conductance. That table is like this. This gives you throw some light or light to you. The common emitter mode, which is most common. Current gain will be something like minus 40 to 50 if HFE is 100, right? And this is called high. Voltage gain will be minus one. Minus means the phase will be reversed, right? Minus doesn't mean attenuation. Voltage gain is also high. And input resistance is 1 kilo ohm. It is medium. Less than 1 kilo ohm, around 500 or 200 ohm, we would call it very good, because we want input resistance to any electronic circuit should be very low. And output conductance is 25 kilo ohm. This is also medium high. It is not at all low, or not very high also, but this is okay. In common emitter mode, all these four parameters, they are practically very good. Current gain is also high, voltage gain is pretty high, input resistance is low side, I should say, output resistance is also high. But in common base mode, there are common base amplifiers also, although in practice, very small use. In common base mode, current gain is low, is less than 1, because common base current mode is alpha, which is 0.9899, something like this. But common base mode circuit is so designed that voltage gain is high, same as the common emitter mode. Common base mode is really low, only 20 ohm, and its output impedance is much higher than this. So if you talk about the input-output resistance, common base mode is better. And voltage gain is also more or less same, but current gain is very low. Now coming to common collector. Common collector, current gain is high, 47. 46, 47 is same as common emitter mode. Its voltage gain is very low. So common collector circuit is not used for voltage gain. It has got some other specific use that we shall discuss when we discuss the common collector amplifiers. Common collector input resistance is very high, 140K. But common collector output resistance is very low, 80 ohm. So these are typical values. Mind it, these are not the values of your transistor, of your amplifier. These are typical values. Just to give you an idea that what should be the expected value. For example, common base current gain is 0.98. But if you design and calculate and find out a value of 98, then you know there is something wrong. These are indicating values. So we have learned how to derive the four important performance parameters of an amplifier with the help of or in terms of its H parameters. And also we have seen what are the typical values. Next, this is a common base BJT amplifier. As I said, its use is very rare, but since it is in your syllabus, you need to learn, or at least you need to see the picture of it. And but its application is very rare. So this is a common base amplifier. Here I have seen the base is connected to the common. current is concerned. Base is current connected to the common, but there is a resistance. So why we call it common base? Because so far as the signal is concerned, this path is short circuit. So this point you must remember. When we say common base, it means the base is connected to common so far as the signal voltage is concerned, which is which is of some frequency 1 kilohertz to many, it could be many megahertz, right? But it is, we are not, common base means we are not talking about the DC common. We are not talking that the base is directly connected to the common. DC is not being discussed. It is only being discussed point is the AC. For the signal, the base is connected to common. So it's a common base. Next is, now you have seen the base bias is same way by your R1, R2 and to the VCC. If you remember common emitter configuration, it is the same biasing configuration. And also, similarly, power supply is given to the collector through a collector resistance RC. So this part is same as the common emitter part, only the shape of the circuit is little different. Either earlier it was a vertical shape, now it's a horizontal shape. And estimated load resistance is also connected here, just like in common emitter configuration. And there is a coupling capacitor CO. Now in common base mode, the voltage gain will be similar to common emitter amplifier because the circuit is really same, basically remains same. But current gain will be slightly less than 1 because what is the current here? It is the collector current. And what is the current here? It is the emitter current. And collector current and emitter current is more or less same. In fact, collector current is slightly less than emitter current. So current gain is slightly less than 1, right? Since input current is IE and output current is IC or collector current. Fine. So I think this is the common base BJT amplifier. We shall, in our next lesson, we shall actually test these kind of amplifiers by simulation software. Common collector. See this collector. Now there is no resistance. It is directly connected to VCC. And also I told you, I think you remember, that any DC supply, any battery is a short, it works as a short circuit so far as the AC signal is concerned. So this AC signal from here, from this battery, it will directly come back to the common. So many students ask me, so why, how it is a common collector? Because collector is here. But the first signal current will go from here to the VCC is the battery or a power supply. Through that battery, it will come back to the common because other end of the battery is connected to common, which is not shown in this diagram. This is a common collector BJT amplifier. And common name, there is a commercial name of this amplifier. It's called common emitter, right? Sorry, it is not called common emitter. I am very sorry. This is not correct. This is called emitter follower. Emitter follower. If I want to correct it, then I have to go out of this thing. So I don't want to correct it. Now, okay, let me try it. This is called emitter follower. I made a mistake. Emitter follower. This is a emitter follower. This is called emitter follower. Why it is called emitter follower? Because this output is taken from the emitter. Earlier, the output was taken from the collector. In both common emitter and common base mode, common base mode output is taken from the collector. Common emitter also output was taken from the collector. right? But common emitter mode or emitter follower output is taken from the emitter. And why it is called follower? Because the potential difference between this base point, between potential difference between this point and this point is only VB base emitter junction voltage. So output voltage VO will always follow the input voltage. There will be no amplification. And that is why it's called emitter follower. Then you may ask me, what is the use of this amplifier? Let's see, what is the use of this amplifier? This circuit, bias circuit, etc., is similar to common emitter circuit, but there is no collector resistor RC and output is taken from the emitter. So that is the difference from a common emitter amplifier and the common collector amplifier. Second point. Here, what is the RDC? Do you remember your biasing lessons? RDC, RAC, you know, here RDC is the current flowing from here to here is only RE. And for RAC, AC current flowing from here to here is this one branch and there is another branch. RAC is RE plus RL. In biasing, you remember there was also an RAC and RDC. There was a DC load line, AC load line. So here also similarly there will be AC load line, DC load line, but RDC and RAC values I have shown you. Biasing techniques. So this biasing technique is exactly same as the common emitter configuration. As we have learned biasing technique in very much detail. If you have RDC, RAC, you can perfectly design your bias. Now consider the input equivalent circuit. This also you have seen earlier. The potential divider here creates a voltage VBB at the base, and these R1, R2 in parallel poses as a Thevenin equivalent of RB. Consider this equivalent circuit. Here what you find? VO from this circuit, VO is equal to VBB. This is the potential VBB minus VBE, junction voltage. So this is the DC condition. DC voltage VO. This, you suppose you have VBB bias voltage 5 volt, and this is 0.7 volt, and so this will be 4.7 volt, 4.3 volt. You cannot avoid this, it will be like that. If that is so, then if you superimpose a signal which is meant V small VO, then VO plus small VO plus VI minus the same VBE. So VI is the input here. So now earlier your input potential was VBB. Now it is VBB plus VI, DC part and AC part. Output is also DC part and AC part. VBE, junction voltage, has no AC DC. So from here what we find, if you compare this equation and this equation, what you find? ACVO is exactly equal to ACVI. That means ACVO equal to exactly ACVI. That means output is exactly equal to input. Right? Then where is the amplifier? Then what is the benefit of this? Some special benefit for the load, or this load. This load is somebody else's equipment. And you know, if you have any equipment and if you want to connect it to the output of another equipment, then you always want the output resistance of that equipment should be lowest possible. Always, that is what you want, and why that you have learned in your circuit theory classes. For the load, output impedance is only Re. And we have seen right from beginning of biasing configuration, Re value is very low, of the order of 100, 150 ohm. So here, for your friend who has come here with the load resistance, he will like your amplifier because your amplifier output resistance is very low. Output impedance is very low, Re. And second point, remember the value of Rb is equal to Re by 10. That is to ensure beta stability of the bias. If you make that calculation, the Rb value becomes moderately high, between 5k ohm to 6k ohm, right? And if beta stability is not very important factor, then Rb can be made still higher. You can make Rb 50 kilo ohm or so. Now, input impedance for this amplifier is Rb. So Rb can be very high. So you have got an amplifier whose input impedance is very high and output impedance is very low. So your friend who have come with the load equipment, he will like it. And your another friend who wants to connect his equipment to your equipment, he also will like it because your input impedance is very high. That is why we always want for a voltage performance, input should be very high, input impedance should be very high, output impedance should be very low. So this special configuration, common emitter, or sorry, not common emitter, emitter follower, it provides this special facility. So it provides an excellent isolation between two stages. You know, uh, later on, if you really go into analog circuit design, very often you have to create an isolation stage. Suppose you have created an amplifier, all these things, and finally you find your output impedance is high, but your output impedance should be low. If your high output impedance equipment is connected to your friend's equipment, then there will be disturbance. So at the end of it, you connect a emitter follower. What emitter follower will do? Emitter follower will not provide any voltage gain, but it will convert this high impedance to low impedance output. And that is called a isolation stage, right? So this is actually common base and common collector mode. And common collector BJT amplifier is more known as emitter follower. I think this is where we end it. And once again, I request you, if you are even slightly benefited by my humble effort, please help me by subscribing to this channel. And today we thank you. And next day, I'll test these common base, common emitter, this kind of amplifiers in actual software simulation. Okay. Thank you.